2 videos in, we've built the limit and we've built continuity. Today we get the payoff. Everything in those 2 episodes has been pointed at one specific limit, the limit that defines the derivative. That's where we're headed. The plan: state the problem the 17th century could not solve, watch a secant line turn into a tangent line as we squeeze it, write down the formal definition in both of the standard forms, tell the Newton and Leibniz story briefly, and then compute 2 derivatives from scratch using nothing but the definition. Along the way, we'll prove that any function with a derivative at a point is automatically continuous there, and meet the classical counterexample showing that the converse is dead wrong. 2 problems sat unsolved for 2,000 years, and both got cracked by the same trick in the late 1600s. The first one is physical. Drop a stone. Its position is some function of time. For free fall near the surface of the Earth, that function is 1/2 gt squared. What is the velocity at, say, exactly 1 second into the fall? Average velocity is rise over run. Take the position at 1 second, subtract the position at 0 seconds, divide by the time. Fine. But that's average velocity over a whole second, not the velocity at 1 second. The second problem is geometric. Draw a curve. Pick a point on it. What's the slope of the line that just grazes the curve at that point, the tangent line? You can draw a secant by picking 2 points and connecting them. The secant has a perfectly good slope, but that's a slope between 2 points, not at 1 point. Same problem, 2 costumes. Both ask for a slope or a rate at a single point, and both seem to ask the impossible, because at a single point there's no run to divide by. Start with what we can do. Pick a point A on the x-axis and let the corresponding point on the curve be a comma f of a. Pick a second point a little further along at x equals a plus h. The corresponding point on the curve is a plus h comma f of a plus h. Draw the straight line through those 2 points, that's the secant line. Its slope is rise over run. The rise is f of a plus h minus f of a. The run is just h, because that's the horizontal gap between the 2 x values. So the secant slope is f of a plus h minus f of a, all divided by h. That fraction has a name worth remembering, the difference quotient. It is the average rate of change of the function f over the interval from a to a plus h. If f is position and x is time, this is average velocity. If f is the height of a curve and x is horizontal distance, this is the slope of a chord. No limits, no mystery, no philosophy. 2 points, divide rise by run, you get a number. The trick now is what happens when we make h smaller. Now the move that took 2,000 years. Hold the first point fixed and let the second point slide along the curve toward it. That means letting h shrink to 0. As h shrinks, the secant line, anchored at the fixed point, rotates. A fan of secants, each pivoting around the same point, all of them sweeping towards something as h gets smaller. That something is the tangent line. The line that just grazes the curve at a. The slope of the tangent line is, by definition, the limit of the difference quotient as h goes to 0. Look at what we did. We never wrote down a slope at a single point. We took a quantity that makes perfect sense for 2 distinct points, the average rate of change, and asked what number that quantity approaches as the 2 points slide together. That's the epsilon delta limit machinery from episode 1, applied to the only quantity that already gave us a sensible slope. Limits don't care about the value at the single point. They care about what's approached. And what's approached, here, is the slope of the tangent. Here's the definition, finally, in print. F is differentiable at the point A when the limit, as h tends to 0, of f of a plus h minus f of a all over h exists as a finite real number. When it does, we name that number f prime of a, and we call it the derivative of f at a. There's an equivalent way to write the same limit, and you'll see both in textbooks, so it's worth meeting both. If you let x stand for a plus h, then h is x minus a, and as h tends to 0, x tends to a. The same definition turns into the limit as x tends to a of f of x minus f of a all over x minus a. 2 notations, identical content. The h form is usually a little easier algebraically because you can expand f of a plus h with whatever rules f gives you. The x form is closer to the geometry. The difference quotient looks more obviously like rise over run between 2 named x values. Use whichever is easier on a given problem. Now the history, briefly. We covered the broad strokes of the Newton-Leibniz story in episode 1, and a longer treatment is waiting in the fundamental theorem episode on the integral side of the playlist. The derivative was invented twice in the late 1600s. Isaac Newton got there first. In 1665 and 66, holed up at his mother's farm at Woolsthorpe Manor while Cambridge was closed for the plague, he developed what he called the method of fluxions. A fluent was a quantity flowing through time, what we'd call a function. The fluxion of a fluent was its instantaneous rate of change, what we'd call the derivative. He wrote it with a dot over the variable, x dot, and physicists in mechanics still use that notation today. To actually compute a fluxion, Newton wrote down something that looks like our difference quotient. He introduced a small quantity he called little o, played some algebra with it, and at the end set o equal to 0 so it would vanish. The answers came out right. The reasoning didn't. That's the move Berkeley would savage 70 years later in The Analyst, calling those little o's the ghosts of departed quantities. The piece that matters now, Newton invented the right thing and could not defend the steps. Across the Channel, in Paris, during his years as a young diplomat, Gottfried Wilhelm Leibniz arrived at the same idea by a different route, somewhere in the 1670s. He published first, Newton sat on his work for decades. Leibniz's central contribution was as much notational as mathematical. He invented the symbols we still use 3.5 centuries later. The dy over dx you write for a derivative is his. The elongated s of the integral sign is also his. He thought of dx and dy as infinitesimal increments, small enough to neglect their higher powers, but non-zero enough to divide one by the other. Philosophically as shaky as Newton's O, practically brilliant. The notation made the symbolic algebra of calculus run on rails. Newton and Leibniz almost certainly invented their machinery independently, but their followers, and eventually the two men themselves, spent decades in a vicious priority dispute. The Royal Society, with Newton serving as its president, convened a committee which ruled in Newton's favor. Newton wrote the committee's report himself, anonymously. We covered the full drama in the fundamental theorem episode. The relevant fact for today, two notations survive. The prime mark f prime from Lagrange a century later, and the Leibniz dy over dx. Both are in active use and you should be comfortable with either. The foundation stayed rotten until the 1820s, when Augustin Louis Cauchy, pronounced Cauchy, laid down a modern derivative definition in his lectures at the Polytechnic School in Paris. The limit foundations went into his course of analysis in 1821. The clean limit of difference, quotient derivative definition is the headline of Lecture 3 in his summary of lessons 2 years later. We met him in Episode 1. What he did for the derivative is what he did for the limit, traded the dubious infinitesimal for an honest limit. In Cauchy's formulation, the derivative of f at x is the limit, as a small quantity he wrote as little I tends to 0, of f of x plus I minus f of x all over I. That's our modern definition. The little I is just our h. No mystical infinitesimal anywhere in the statement. A function, a difference, a quotient, and a limit, all well defined in terms of the epsilon delta machinery from Episode 1. Karl Weierstrass tightened the foundations a generation later in Berlin, but the move that put the derivative on real footing was Cauchy's. The definition in every modern textbook is essentially his. Three notations are in active use, and you'll meet all three. First, Lagrange's prime notation, from the end of the 1700s. F prime of a for the derivative at a, f prime of x for the derivative as a function. Compact, clean, best when you want to treat the derivative as a function in its own right. Second, Leibniz's notation. df over dx, or dy over dx if y is f of x. To indicate the value at a particular point, you bar the expression and write x equals a underneath. Heavier on the page, but it pays for itself the moment you do multivariable calculus, related rates, or differential equations, because it shows you what you're differentiating with respect to. Third, Newton's dot notation, x dot for the derivative of x with respect to t, almost exclusively used by physicists for time derivatives. All three refer to the same number. The skill is reading any of them. Time for an actual derivative. Take f of x equal to x squared, and let's compute its derivative at a completely general point a, using nothing but the definition. The whole point is to watch the machinery move. Start with the difference quotient. F of a plus h minus f of a over h becomes the quantity a plus h squared minus a squared, all divided by h. The numerator first. Expand a plus h squared. That's a squared plus 2ah plus h squared, middle school algebra, FOIL, or the binomial theorem, take your pick. Subtract the a squared sitting at the end of the numerator, and the two a squared terms cancel. What's left in the numerator is 2ah plus h squared. Now look at the denominator. It's an h. And every term in the numerator has an h in it. 2ah has one factor of h squared has 2. Factor the h out of the numerator, you get h times the quantity 2a plus h. The h on top and the h on the bottom cancel. For every non-zero h, the difference quotient is just 2a plus h. We are still working away from h equal to 0. Limits, since Episode 1, only care about behavior near 0, not at 0, so canceling that h is completely legal. Now take the limit. As h tends to 0, 2a plus h tends to 2a. So the derivative of x squared at any point a is 2a, and the derivative function is 2x. Pick any point on the parabola y equals x squared. Drop the x-coordinate into the formula 2x, and that's the slope of the tangent line right there. At x equals 0, slope 0, the vertex where the tangent is horizontal. At x equals 1, slope 2. At x equals 3, slope 6. Sanity check that one by drawing a line of slope 6 through 3, 9. It grazes the parabola without cutting through. By the way, 2x is the simplest case of the power rule. Next episode, we'll prove that the derivative of x to the n is n times x to the n minus 1 for any positive integer n by essentially the same algebra. The power rule is a shortcut built on this calculation. If you ever forget it, you can rederive it from the definition. The definition is the bedrock, the rules are toolbox items. A second example, more interesting algebraically. Take f of x equal to the square root of x and compute the derivative at a strictly positive point a. We need a positive, since square root isn't defined for negative x. The difference quotient is the square root of a plus h minus the square root of a over h. Plug in h equal to 0 and you get 0 over 0. The factoring trick from the last example doesn't work. There's no obvious h factor on the top. The move for this kind of expression is something you've probably seen in pre-calculus. Rationalize the numerator. Multiply top and bottom by the conjugate. The same expression with the minus sign flipped to a plus. The numerator becomes a difference of squares, square root of a plus h squared minus square root of a squared. The squares and square roots annihilate, leaving a plus h minus a, which is h. So the numerator is h, the denominator is h times the sum of the two square roots, and the h's cancel. For every non-zero h, the difference quotient is 1 over the square root of a plus h plus the square root of a. Now take the limit. As h tends to 0, the square root of a plus h tends to the square root of a. Square root is continuous on the positive reals, a fact from the continuity episode. The two square roots in the denominator collapse onto the same number, and their sum is 2 times the square root of a. So, the limit is 1 over 2 times the square root of a. The derivative of square root of x at any positive a is 1 over 2 times the square root of a. Quick sanity check. At a equal to 4, the formula gives 1 over 2 times 2, or 1/4. So the tangent line to the square root curve at 4, 2 has slope 1/4. Move 1/100th of a unit to the right. The tangent predicts a rise of 1/4 times 1/100th, which is 25 10,000ths. Actual value, the square root of 4.01 is about 2.0025. The actual rise is 25 10,000ths, exactly what the tangent slope predicted. The definition is doing what it advertises. A short theorem with a satisfying proof. If f is differentiable at a, then f is continuous at a. In words, having a derivative at a point is enough, by itself, to guarantee continuity at that point. Let me show you why. We want to prove that the limit of f of x as x approaches a equals f of a. That's the definition of continuity. Equivalently, we want the limit of f of x minus f of a to be 0. Here's the slick move. For any x not equal to a, write f of x minus f of a as the difference quotient times x minus a. That's not a trick, it's an identity. You're multiplying and dividing by x minus a, and it's allowed because x is not a. Now take the limit as x approaches a. The first factor is the difference quotient. By assumption, f is differentiable at a, so that limit exists and equals f prime of a. The second factor is just x minus a, which tends to 0. By the product law for limits, the product of those two limits is f prime of a times 0, which is 0. So the limit of f of x minus f of a is 0, which means the limit of f of x as x tends to a is f of a, that is continuity. Done. The intuition, a function with a tangent line at a point can't be jumping at that point. If it jumped, no straight line could capture its behavior on both sides simultaneously, and the secant slopes from the two sides wouldn't agree. Differentiability is, in some sense, a stronger and pickier condition than continuity, worth filing away. The converse of that theorem is false, and the cleanest counterexample fits on a postcard. Take f of x equal to absolute value of x. Continuous everywhere. Its graph is the classic V, two rays meeting at the origin, no jumps. But not differentiable at 0. Plug 0 into the definition. The difference quotient at 0 is absolute value of h over h over h. If h is positive, absolute value of h is just h, so the ratio is 1. If h is negative, absolute value of h is minus h, so the ratio is minus 1. Right-hand limit plus 1. Left-hand limit minus 1. They disagree. By the existence theorem from episode 2, the two-sided limit at 0 doesn't exist, so f prime of 0 doesn't exist. Geometrically, the graph has a corner at the origin. The curve is asking you to pit between two slopes, and a tangent line only has one slope. So differentiability is genuinely stronger than continuity. Continuous functions can have corners. They can even, as Karl Weierstrass demonstrated in 1872, fail to be differentiable at any point at all. He constructed a continuous function on the real line whose graph wiggles so badly that no point on it has a tangent line. Continuous everywhere, differentiable nowhere. Most mathematicians had quietly assumed continuous functions were tame. They aren't. Why is this one limit worth a whole video? because everything we'll do for the next 10 episodes is built on top of it. Next episode, the power rule, the sum rule, and the constant multiple rule. Each one a theorem proved from the definition, not an article of faith. After that, the product rule and the quotient rule. After that, the chain rule. Each rule is a labor-saving device that lets you avoid going back to the definition every time, but it only works because the definition was made to do the work first. The derivatives of sine, cosine, the exponential, the natural logarithm, all derived from this definition once and tabulated for everyone else. Implicit differentiation, related rates, linear approximation, the tangent line approximation engineering leans on every day. All of them are the definition in different costumes. The mean value theorem, the extreme value theorem, optimization, Newton's root, finding method. Everyone sits on this definition. And when you cross over into integral calculus, the fundamental theorem of calculus tells you that the derivative of an integral is the original integrand. That statement is, at its heart, about the limit you saw today. The definition isn't just the starting point for differential calculus. It's the hinge between the two halves of the subject. We landed. Average rates of change are easy. Pick 2 points, divide rise by run, you've got a number. Instantaneous rates of change are not easy because at a single point there is no run. The trick is to take a limit of the average rate as the 2 points slide together. That limit, when it exists, is the derivative. Newton invented this in the 1660s at Woolsthorpe with his ill-defined little o Leibniz, reached the same machinery in the 1670s in Paris with his dy over dx. Their followers spent decades arguing over priority. Cauchy in the 1820s finally put the whole thing on the limit from episode 1, where it has lived ever since. Differentiability at a point implies continuity at that point. The proof is one line at algebra and the product law for limits. The converse is false. Absolute value of x at the origin is continuous but not differentiable, with a corner that no single tangent line can resolve. 2 derivatives done from the definition. The derivative of x squared is 2x by expanding the binomial and cancelling. The derivative of square root of x is 1 over 2 times the square root of x by rationalizing the numerator. Next episode, we stop computing derivatives one at a time and start producing them by rule. The power rule, the constant multiple rule, all derived from the definition you just learned. The foundation that, from here on, you'll be standing on without thinking about it. See you there. A derivative measures how fast something is changing at one single instant. The way this channel changes at one single instant is 1 like, 1 comment, 1 share at a time. Thanks for being one of those instants. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.